All right, let's go ahead and begin. So chapter 18 is about using enolates as nucleophiles, but this time instead of doing an SN2 reaction and using some alkyl halide as an electrophile, this time our electrophile is going to be another carbonyl compound. So we're bringing together all of the worlds we've been sort of swimming in so far. And the first reaction we're going to talk about that does this is called the aldol reaction. The al is for an aldehyde, though you do this with ketones as well, and the ol is for the product, which tends to be an alcohol. All right, so just as a little bit of background, we've said that for a typical ketone, you've got a proton with a pKa of around 20, such that if you put this molecule in a solution of sodium hydroxide, you've got a very small amount of enolate, and you can tell that it's a very small amount of enolate because of the difference in pKa between the acid on this side of the equation and on this side of the equation. So here is an enolate. We know enolates are nucleophiles, and equilibrium favors the ketone. The enolate itself is in equilibrium with the enol conjugate acid, which is a tautomer of the ketone. And then, of course, you have also over here in some amount, it depends on how electrophilic the ketone is, you have some amount of the ketone hydrate. All of that stuff we've talked about already, but basically in aqueous solution, if in basic aqueous solution, you've got some of all of this. Though, if we were to compare, the ratio of these two, it's probably something like greater than 99% ketone and less than 1% enolate. Okay? All that looks vaguely familiar. What we haven't considered, but what we will consider today is if you have some enolate, can that then react as a nucleophile with your ketone, which is an electrophile? So this is the aldol reaction. You take the enolate and you react it with some of the starting ketone. You can push arrows in a number of different ways. Remember that the enolate has the following resonance structure, which puts the negative charge on the alpha carbon. You can have that alpha carbon attack the ketone directly at the carbonyl carbon to break the pi bond, as we've done previously, or you could have electrons kicked down to form a carbon-oxygen pi bond and then have the pi electrons move onto the alpha carbon and attack the carbonyl carbon. Either is okay. They're just resonance structures of the same alternative. So you basically have, as we did in chapter 17, an enolate nucleophile. Now it's reacting with a ketone electrophile. So you're going to have to use what you learned in chapters 13 through 16 to know what to do when a nucleophile attacks a ketone. And you're going to have to use what you learned in chapter 17 to know what to do as a nucleophile attacks, as an enolate nucleophile attacks an electrophile. You can follow through the conclusions. This part of the molecule is from the nucleophile or the enolate. Here is the new bond we formed. And then here is the tetrahedral intermediate. As we did in chapters 13 through 16, what happens next depends on whether we have a good leaving group or not. We can it is possible for a negatively charged oxygen to kick off an enolate as a leaving group. The enolate's not a particularly good leaving group. Nevertheless, the backwards reaction here is known. So, if the negatively charged oxygen in the tetrahedral intermediate kicked the enolate off as a leaving group, we would just go back to starting materials. The other thing that can happen is this reaction takes place in water, as noted above. And so we can protonate that negatively charged oxygen using water to give the following product. And I want to talk about the structural features of this product because you're going to need to get good at recognizing this. Here is a carbonyl carbon. Here is the alpha carbon. Here is the beta carbon. In this reaction, we have just made a carbon-carbon sigma bond between alpha and beta carbons. And our product is a beta hydroxy carbonyl compound. So that's a structural pattern to look for, because when you see it, that means you could have made this product via the aldol reaction. Now, the arrows show that this is an equilibrium reaction, which means that you can start with the aldol product and you can go back to ketone starting materials. In any case where equilibration is possible, you can control which direction the reaction goes based on reaction conditions. Yes?
Put the lone pairs on the enolate oxygen.
Could the lone pairs on the oxygen attack as the nucleophile? And the answer is generally not, because of something I mentioned last time. It's a consequence of molecular orbital theory. Most of the highest occupied molecular orbital is actually on the alpha carbon. Yeah, so that's the one that's going to be doing the nucleophilic attack. All right, what else? Okay, so that beta hydroxycarbonyl compound is one of is an aldol product, but sometimes that aldol product goes on to form this alpha beta unsaturated carbonyl compound instead. Take a look at this. Both of these are considered aldol products. Whether you stop at the beta hydroxy carbonyl compound or go on to the alpha beta unsaturated carbonyl compound really depends on context, and your text doesn't really give you any tools for that. So if I were to ask you to show an aldol product, I would have to accept either of these as options. What do you notice? What's missing from compare the beta hydroxycarbonyl compound to the alpha beta unsaturated carbonyl compound? What do you notice is missing? Go ahead. The OH group, good. And was there something else that's gone? Yeah, the hydrogen. It's a dehydration product. And the mechanism of this dehydration product is known. It's neither E1 nor E2. As you could imagine, the proton that's alpha to the carbonyl group and adjacent to the OH group is going to be more acidic than a typical proton. Nevertheless, there's good evidence that first, the OH group removes the proton on the alpha carbon to get to another enolate intermediate. and that's a resonance stabilized enolate. And then these electrons finally, in a second step, kick down and kick off the OH group, and that gives you your dehydration product. In this reaction, it's thought that the first step is fast. Removal of the proton is fast, whereas leaving of the OH minus leaving group is slow. This reaction mechanism where, because it's the second step that's slow, this reaction is technically an E1 type elimination reaction because it is unimolecular, but it's a special kind of E1 reaction. Unimolecular means the concentration of base doesn't matter, only the concentration of your starting material. But you do have to deprotonate first, and so this is often called an E1CB reaction, where CB is for conjugate base. This is the other extreme of an E1 reaction. Do you remember in 351 when doing an E1 reaction first, the leaving group would leave to give you a positive charge, and then and only then the base would come in and do the elimination? In contrast here, the leaving group doesn't leave until the base does its job. So you get the conjugate base first, and then it's an E1 reaction. That's sort of a minor mechanistic detail. We'll refer back to it. It's not, I'm not going to really push you on what is the definition of an E1CB reaction. The thing that allows you to remove the proton first is the fact that the intermediate is resonance stabilized, and because OH minus is not that good of a leaving group, it takes a while to leave. So you form the conjugate base first, and then the leaving group leaves. Yeah?
Does that allow for time to put anything else on the carbon?
Could you do subsequent reactions putting things on the carbon? Yes, you can imagine a whole bunch of complexity there. We're not going to worry about that, but you're right to be thinking about it. So both of these, the beta hydroxycarbonyl compound and the alpha beta unsaturated carbonyl compound, are legitimate aldol products. Whether you get one versus the other, because they're in equilibrium, it's simply going to depend on their relative stability. So I don't have any good predictive tools for you to know which one should I draw. Draw both, recognize both. Yeah?
On an exam, would you want us to draw both?
Well, you're not going to be drawing anything on my exams because they're multiple choice. But what that means is if the beta hydroxycarbonyl compound is A and the alpha beta unsaturated carbonyl compound is B, both of them have to be right. Read the instructions to know whether you need to select all that apply. But I'm not going to actually try to trick you up on, well, which one should I pick? Because I told you now that they're both aldol products. Yeah. Which means in a predict products aldol question, I should just show you one of them so that you don't get confused. All right, what else? Yeah. Does that only happen under basic conditions? I've shown you the aldol happening under basic conditions. You can do it under acidic conditions, but I don't. You can draw an elimination or dehydration reaction under acidic conditions too. I think, yeah, E1CB, because it involves removing the proton first, that's probably a basic conditions only thing. I don't recall your text making a big deal out of that, so I don't think we will either. All right. What I've shown you here is the self-aldol reaction, in the sense that we had one starting material, the ketone, and one equivalent of ketone was our electrophile, and one equivalent of ketone was the enolate nucleophile. This is the portion of the molecule that ends up being from the enolate. And this is the portion of the molecule that ends up being from the electrophile. And the bond you make, whether you're looking at the alpha beta unsaturated carbonyl compound or the beta hydroxy ketone, the bond that you made in this reaction is the carbon-carbon bond between alpha and beta carbons. Single bond for the beta hydroxy carbonyl compound, double bond for the alpha beta unsaturated one. Okay. Let's talk about the retroaldol reaction, because this retroaldol reaction is important in biology. It can also help you in synthesis questions to be able to look at an aldol product and think, what were the starting materials? So I'm going to actually start with that alpha beta unsaturated carbonyl compound, and we're going to take it all the way back to the enolate and ketone, carbonyl carbon, alpha carbon, beta carbon. Notice as we go through this, the intermediates we use are going to be exactly the same. We're just going to push arrows in the opposite way. So the final step was E1CB style elimination of an OH group, breaking the bond between the beta carbon and the OH group. Therefore, step 1 of the retroaldol reaction is conjugate addition of OH at the beta carbon. We talked before about how in alpha beta unsaturated carbonyl compounds, the LUMO is on not only the carbonyl carbon, but also on the beta carbon. We've seen cuprates do this before, and for the retroaldol reaction, we will now see OH do it. So we have the OH attack the LUMO at the beta carbon, and these electrons move on to the alpha carbon to give me the following intermediate. Go ahead and convince yourself that that is the same intermediate that we drew immediately before. Then, what's the intermediate before that one? It's the one where we just have no enolate, just the regular neutral molecule. So to get from there to here, we simply need to use water as an acid, and that will get us to the beta hydroxy carbonyl compound. So that's backwards from the alpha beta unsaturated carbonyl compound to the beta hydroxy carbonyl compound. If you look at where we went previously, before we got to that, we had our negatively charged tetrahedral intermediate. So we will get to that negatively charged tetrahedral intermediate simply by having hydroxide remove the proton from our beta hydroxy ketone. That gets us to the tetrahedral intermediate. Now to do the retroaldol, we simply need to do what I told you up here, which is negatively charged oxygen kicks electrons down and kicks the enolate off. And you can draw that enolate in either of the two resonance structures that we've used before for these things. So again, this portion was the electrophile, this portion was the enolate. All right, questions about that? Yeah.
We could do this with an aldehyde too.
Oh yeah, you can do this with an aldehyde too. We just chose the ketone as an example. All right. So one thing that people, I find that it's difficult for people to look at an alpha beta unsaturated carbonyl compound and say, wow, that's an aldol product, in part because the oxygen from your electrophile portion is no longer in this molecule, so it's going to take some practice till you're able to see that really well. Where does that oxygen go? Well, it leaves in this E1CB step. It leaves as this OH group. I'll show you a biological example of a retroaldol reaction a little bit later. Why not? Let's do it now. So this is from glycolysis, which is metabolic series of reactions that breaks glucose down into something that can go to the citric acid cycle. What I'm drawing for you now is not a structure to memorize yet. This is, and its name is also not something to memorize yet, but I'm going to write it down so that when we deal with it again in the future, you'll remember having seen it before. This is fructose 1,6-bisphosphate. One, two, three, four, 5, and 6. Oops. Now, take a look at that structure and find for me the atom numbers that correspond to an aldol product. Okay, we're working on the skill of not being overwhelmed with big molecules, but focusing on the right functional groups. The aldol product is either an alpha beta unsaturated carbonyl compound or a beta hydroxy carbonyl compound. Do you see that here? Your ketone, and then where is the beta hydroxy group? Alpha, beta, right? Or alternatively, let's just use, sure, we can use purple. Carbonyl carbon, alpha carbon, beta carbon. Which means that this bond between alpha and beta carbons could have been made via an aldol reaction, and that bond can be broken by a retroaldol reaction. It may be helpful here to draw in protons that were implied but not originally shown. So in biology, what happens, the first step of a retroaldol reaction starting from the beta hydroxy carbonyl compound, if you look above, the first step of the retroaldol was deprotonate the beta OH group. So there's the beta OH group. You're going to use some base from the enzyme, we don't care what it is, to remove that proton. Now, the next step of the retroaldol reaction is electrons kick down to restore the carbonyl here, and then we move these electrons from the bond between alpha and beta carbons. We'll move those electrons onto the alpha carbon to get a resonance stabilized enolate. This is our electrophile, right? This happens to be called glyceraldehyde 3-phosphate. And then what's left in our other portion of the molecule is this. An enolate, which can then pick up a proton from some source. The enzyme is fine. And then that becomes what you will later learn is dihydroxyacetone phosphate. So this is a key step in glycolysis. It takes a 6-carbon precursor and breaks it up into 2 3-carbon precursors, which you can then do subsequent reactions with. Yeah?
Yes, you kind of answered that. Is that how the enzyme aldolates?
That's aldolase, yeah. Yep, if you've heard or memorized the enzyme that catalyzes this reaction, it's called aldolase. It's not called retroaldolase because enzymes don't care which direction the reaction goes, so you just pick one. And they picked the backwards reaction, which is would be reacting the enolate of dihydroxyacetone phosphate with glyceraldehyde 3-phosphate to get fructose 1,6-bisphosphate. But yeah, it catalyzes the retroaldol reaction. Okay. How you feeling about that? Pretty overwhelmed? Okay. If you feel overwhelmed by stuff, feel free to go back through and abbreviate. For example, let's see. That might make it simpler, less to worry about. Heck, you can even forget that this OH group is there and abbreviate that too. Feel free to abbreviate anything that's not immediately involved in the reaction, and maybe it's clearer or easier to see the the beta hydroxycarbonyl compound. Okay. It gets worse. So much worse. What I showed you has been the self-aldol reaction. Naturally, we're going to want to make it more complicated. So we're going to start with the worst, and that is the intramolecular aldol. Which is your favorite thing and mine, making a ring. All right, so here we have a molecule that has some symmetry. The 2 carbonyl groups on either end are identical, so it doesn't matter which one we start with. All right? So let's draw the 2 enolates we could potentially form if we reacted this OH group and removed one of the protons. You've got basically two different kinds of alpha protons, right? You've got this less substituted one and this more substituted one. So presumably you could make either, and maybe we'll sort of make the arrows uphill so we remember that enolates are higher in energy than ketone starting materials. Let's go with purple enolate here. And I'm going to draw the structure with the negative charge on the alpha carbon just because that's where it's going to react. And then over here we'll draw orange enolate. All right. Now if we had to pick, we'd actually say purple enolate's a bit more stable than orange enolate. But let's think about what happens next. Okay. You have your nucleophile, your enolate, in the same molecule as you have an electrophile. So you can do an intramolecular aldol reaction. Recall that intramolecular reactions are fast because nucleophile and electrophile don't have to wait around to find each other. They're already connected. So we could push arrows like this. Let's see what kind of ring we would make. You need to just count the atoms. 1, 2, 3, and 4. So we make a new bond between the alpha carbon here and the carbonyl carbon here. And that is a 4-membered ring. So we're going to draw a 4-membered ring. We're going to number the carbons 1, 2, 3, and 4. No, that's actually not how we're going to number them. We made a new bond between 1 and 4. That's here. Carbon 1 was an alpha carbon, alpha to this carbonyl group. And carbon 4 is the one that got attacked, and so it's going to have the negatively charged oxygen from the tetrahedral intermediate, which we could draw getting a proton to form the beta hydroxycarbonyl compound, and we could show that in equilibrium with the alpha beta unsaturated carbonyl compound. Okay. How about here? How about on the other side? What kind of a ring are we going to make there? Enolate attacks carbonyl compound 1, 2, 3, 4, 5, 6. So we need to make a 6-membered ring, so draw a hexagon. Number the atoms 1, 2, 3, 4, 5, and 6. The bond we make is between 1 and 6. 1 is bonded to 2, which has a ketone group on it. 6 is going to be our tetrahedral intermediate with a negatively charged OH group and the methyl group on it, which we could show picking up a proton to form the beta hydroxycarbonyl compound, which could be in equilibrium with the corresponding alpha beta unsaturated carbonyl compound. All right, so you've got 2 options. One through a more stable enolate to a 4-membered ring product. Another through a less stable enolate to a 6-membered ring product. I mentioned before that the aldol reaction is an equilibrium reaction. And you can control formation of, you can promote the formation of aldol products based on the conditions that you use. If it's an equilibrium reaction, the thing that matters most is which is the most stable product, not necessarily which is the most stable intermediate. So, what do you think? 4-membered ring, 6-membered ring. What's the major product? 6, because of ring strain, right? So the 6-membered ring is going to be the major aldol product because it is more stable. So in an intramolecular aldol reaction, you're looking to make the more stable ring. All right. Yeah.
Is that thermodynamically dependent, i.e. getting cold enough where the more stable intermediate is preferred, or it's always going to form it?
Could you do this reaction under conditions where you might generate this, especially if you lower temperature and prevent equilibration? Yes, maybe, though if you lower the temperature, this is the kinetic fastest to form enolate, so that might tend to still keep you going that direction. So, yeah, it's a good question. I'm not sure. All right. So I tried to walk you through the strategy of what kind of ring do you form. It would be probably useful practice for you to start with the ring compound and go backwards to the aldol starting material so that you can see the structural patterns and you know, when you look at something like that, you need to get to the point where you see, oh yeah, that's an aldol product, and sorry, let me just illustrate. If you see something like this, you need to get to the point where you're able to say, oh yeah, easy, that's an aldol product, and I can draw that product, I can draw the starting material that would have led to that aldol product really easily. Okay, it needs to be that fast, so practice until you're able to do that. Okay, so that's the sort of making a ring. We should now talk about what if you wanted to do not a self-aldol reaction, but a crossed aldol reaction. All right, so let's use aldehydes this time. And let's suppose that I want to react this aldehyde with this aldehyde, and my desired product is this one. That is, I want orange aldehyde to be the electrophile, and I want purple aldehyde to be the nucleophile. How well is that going to work? So good, right? No. The problem is that both of them have protons, alpha protons, that are acidic, or rather more acidic than you would expect for an sp3 hybridized carbon. Both pKa's here for aldehydes tend to be around 17, which means that if an OH group hydroxide base sees either of these, there's no selectivity. You're going to make both enolates. And as soon as you make both enolates, you've got a mess because you have 2 nucleophiles and 2 electrophiles, which means that in addition to my desired product, which is a cross aldol product, I'm going to get the other one where my other aldehyde acts as the nucleophile, and my other aldehyde acts as the enolate. So I'm going to get the other crossed aldol product. And I'm also going to get the two self-aldol products. See where each of those comes from? Here is the self-aldol product of the acetaldehyde. Here is the self-aldol product of this other aldehyde that I don't know the name of. Here are the two crossed aldol products. I only wanted one, I'm getting 4, and that's ignoring the alpha beta unsaturated carbonyl compounds that I might also have gotten. So in general, the crossed aldol is a bad idea. But there are some workarounds that your text talks about and that we can review. They're not mind-blowing or anything. They just sort of make sense. So strategy 1 is you use an aldehyde or ketone, use as an electrophile an aldehyde or ketone that has no alpha protons. So that's sort of the strategy. So we'll change the situation just a little bit. We'll use the same aldehyde that we want to use as our nucleophile, only this time we're going to make it so that our electrophile has no alpha protons. Right? So there's no enolate that can be formed there. And that means when you do the aldol reaction, the only enolate, the only nucleophile you're going to have is this one. Now, so that increases your chances of getting your desired product. Your desired crossed aldol product, though it does not get rid of the possibility for a self-aldol reaction. Self still a possibility. And you would just have to hope and maybe pray that the desired crossed aldol product was more stable than the self-aldol product. I'm not drawing the alpha beta unsaturated carbonyl compounds here. Those are legitimate products as well. So you just have to, this isn't a 100% perfect solution, but it does cross some of the complications off the list. You don't, if we use this approach, you never get the products where the second aldehyde was the nucleophile. Not great, but you can do it. Second is to use as your nucleophile a carbonyl compound with very acidic alpha protons, such that there's no contest as to who the enolate is going to be. For example, and actually in retrospect, this is an example of quantitative enolate formation. So if I use this beta dicarbonyl compound whose alpha proton has a pKa of like 9, Then it's 100% yield for hydroxide to remove the proton. To give me, and actually, yeah, I shouldn't use equilibrium arrows, that's 100%. To give me the desired enolate. And I can do this in the presence of another ketone where the alpha proton has a pKa of 20. See, there's no contest. The OH is going to OH minus is going to completely remove the proton from this beta dicarbonyl compound. I'm never going to form the enolate from that other ketone. And therefore, once I've made 100% of the desired enolate, I've got really, really high odds of that enolate attacking the second carbonyl compound. And I'm skipping ahead in the mechanism. I'm going to just show you the beta hydroxycarbonyl product. And here's the new bond that I made between alpha and beta carbons. And the secret was that there was simply no contest between the two alpha protons. All right, the final workaround is another version of that one. Only our focus for workaround 2 is on the identity of the carbonyl compound. Our focus for workaround 3 is basically it's also going to be quantitative enolate formation with LDA as a base. So step 1 is you use LDA to make your carbonyl, you make your enolate in 100% yield. You're going to do this at really cold temperature with an aprotic solvent. So I'm going to write minus 78 C to indicate you're doing this over dry ice. People will use tetrahydrofuran as a solvent. That's just a solvent that doesn't have any acidic protons. You make the enolate in 100% yield. It's only then at that stage that you introduce your carbonyl compound. And hopefully, if you're careful and you run the reaction at low temperature, you don't get enolate exchange. Here I'm choosing an aldehyde that does have an acidic alpha proton. So I have to keep it cold so that this enolate doesn't deprotonate this carbonyl compound. As soon as I form any of that alternative enolate, all bets are off. So this is tricky. But if I'm careful and I keep it cold, I have a pretty good shot, much better than the original crossed aldol attempt, of getting the desired connectivity. The desired molecule is my enolate, and the desired molecule is my electrophile. So experimentally, that's a little bit tricky, but we're going to pretend like it works like a charm 100% of the time. This is called the directed aldol. Because you're using LDA to direct, and you're using careful experimental conditions to direct who gets to make the, whoa, I got the colors backwards, didn't I? Let's try that again. Who gets to be the enolate and who gets to be the electrophile. The idea here is that the second molecule never, ever, ever sees LDA because you've consumed it all by making that first enolate. All right. Questions? Yeah.
How can you use workaround 2 to get your desired product?
To get this one?
Yeah.
Yeah, that one's not, workaround 2 isn't going to apply because our problem was that the two aldehydes had similar pKa's. Our cheat code on workaround 2 is we changed what ketone we were using. So yeah, I mean, I agree, it's not a great workaround for that. It's like we're moving the goalposts there. But if you wanted to do a crossed aldol reaction just to say that you did, this would be a way to do it. All right, other questions? Okay, well, let's take 5. We got another lecture on this subject, but the next one is kind of the thing at the end of all of this is a bit of a doozy, so we want to continue onward and get about halfway through the chapter by the end of today. So, take 5, we'll be back around 9. All right, here we go. So, part 2 is just like the aldol, only we're going to change the electrophile a little bit. We're going to put a leaving group on the carbonyl carbon. And this is called the Claisen reaction. So, I don't care. You have no visual? I'm sorry. I really do care. Let's try that again. We've lost visual. That's better. Sorry about that. I do care. Just one of the most effective ways to diffuse a child asking you for something when they whine about it is to just say, I don't care. Great parenting advice, right? This is not the School of Family Life. This is chemistry. My wife is actually teaching a class right now in the School of Family Life about marriage and preparation for it and all of that stuff. And she's the expert on that. All right. So the Claisen reaction, doing the aldol but with a leaving group. What do we mean by this? Well, let's start with an ester. An ester differs from a ketone in the fact that you've got this alcohol group attached to the carbonyl carbon, or what used to be an alcohol. And the pKa of an ester proton is decently high. I forget what it was. It was in the 20s, or it was in the upper 20s, perhaps 30s. It's reflecting the fact that esters aren't as reactive as ketones. But let's just say that we use some strong base, in this case sodium ethoxide. We are using ethoxide so that we don't have to worry about this base acting as a nucleophile and attacking the carbonyl carbon. If it did, we don't care, because the only thing that's going to happen at that point is you kick off one of the 2 ethoxide groups and you go back to starting material. So again, as we did with that acetoacetic or malonic ester synthesis, we're choosing a base that matches the identity of the group on the ester. Students usually ask, well, what if this is some big, large group that's important? Well, then chances are you wouldn't be doing the Claisen reaction with it. All right, so we're not going to worry about this potential inconsequential side reaction. We're going to first make the enolate of the ester. And again, it's true that that's uphill in energy. So again, you're looking at greater than 99% ester starting material, less than 1% enolate. But the enolate that forms can then act as a nucleophile to attack some of the remaining unreacted ester at the carbonyl carbon. That's going to give you a tetrahedral what are we doing there? It's going to give you a tetrahedral intermediate. And now we're going to do what we did at the beginning of the semester, which is ask what happens to the tetrahedral intermediate. If these electrons kicked down, they could kick back off the enolate, and that would simply be the backwards step. The Claisen reaction, like the aldol reaction, is an equilibrium reaction. But it's also reasonable for that negatively charged oxygen to kick off ethoxide, another negatively charged oxygen, as the leaving group. And when we do, we have this product. Notice its similarities with the aldol product, carbonyl carbon, alpha carbon, beta carbon. We just made a bond between alpha and beta carbons, but the difference is the thing that's on the beta carbon is a carbonyl group. So we just made a beta keto ester. You've seen that before last lecture, by the way. That's the acetoacetic ester that we used in that enolate alkylation reaction series. Okay. Now you can synthesize that. Now, I told you this was an equilibrium reaction, and it is. You could, at this stage, as I said, have kicked off the enolate and gone back to starting material. But the great thing about the Claisen reaction is it has this final kick, final thermodynamic sink that pushes the reaction to completion. As soon as you make the beta keto ester, you now have a proton that's alpha to 2 carbonyls instead of 1. And you've just made that alpha proton have a pKa that's much lower than the pKa of your base's conjugate acid. In other words, as soon as that ethoxide leaves, it steals that proton and then you're at the stage of having this enolate and ethanol pKa 16. That's, again, about 100% yield. So while all of these steps are reversible up to this point, as soon as you lose that alpha proton, the reaction is done. And usually there is some gentle aqueous workup, gentle acidic aqueous workup that's going to be enough to put the proton back on the alpha carbon. When your text shows the Claisen reaction, they will sometimes show it like this. They'll start with the ester. They will use sodium ethoxide, and then they will use H3O+. And what they mean by that is gentle aqueous workup to get you back here. I prefer not to do that because we just went through this whole thing in chapter 17 where we used H3O+ to hydrolyze the ester, then we turned up the heat and decarboxylated the thing. So to distinguish between that, we're just going to assume that gentle aqueous workup is part of the recipe. I'm not going to write it out specifically. That's how we'll write the Claisen reaction. If you want to, you could, of course, add acid, cook this to hydrolyze it, get to the beta keto acid, and then decarboxylate, and then you would have this ketone. That's a whole lot of effort to make acetone, which you could just buy, but you could do it if you wanted to. Yeah?
Would that sodium ethoxide ever deprotonate the ester?
I'm sorry, which ester?
Starting.
Yes, in fact, that's what happens to make the enolate. Yep. Yep, no, that's good. What else? Yeah.
How does the aqueous workup, like where do the electrons go?
You're just adding enough H3O+ to protonate that negative charge without hydrolyzing the ester. Yeah. What else? Yes? Could this go on to do more chemistry on the starting material? That seems reasonable to me. So I think you're asking, well, do you ever make the double beta keto ester? I think that sounds reasonable to me. Your text never goes there, so I can't explain why it doesn't happen. Other than to say that perhaps by the time you get here, there's not a whole lot of unreacted ester left, but that seems unsatisfying to me, so I guess I really just don't know. All right, what else? Yeah.
So that whole step where you remove the proton and then do an aqueous workup, what was the point of that? Was it to show that that negative product can be the product?
The whole, yeah, so I struggle with that too. Why show take the proton off, put it back on? This is to demonstrate that the acidity of this proton drives the reaction to completion. If you have a bunch of irreversible steps, followed by, a bunch of reversible steps followed by an irreversible one, Le Chatelier's principle is going to take you all the way to the irreversible one. Yeah.
And so the irreversible one takes you to?
Takes you to the negatively charged one, so you're not going to go backwards. Then once the reaction's done, you can gently protonate it. Yeah. Okay, but if I were to ask for a mechanism, yeah, there would be no point in showing removing the proton and then putting it back on again. All right, what else? So all the same issues with this reaction, with the aldol reaction apply here. So there is an intramolecular version of the Claisen reaction. Sometimes reactions have their own names. I think your text calls this perhaps the Dieckmann condensation. Condensation, I think, because you're bringing two molecules together. You don't have to memorize names of reactions, and it's fine just to call this the intramolecular Claisen. The Claisen is named after the person who discovered it. Aldol wasn't a person, it was more of a thing. There are two ways that organic chemists like to show off. Well, there's probably multiple ways, but way number one is knowing the names of various reactions. And so if you ever go to an OChem talk, especially by an assistant professor who's trying to impress people, they will be dropping name reactions all the time. And you sit there and you're like, oh yes, the Claisen reaction, because you feel obligated to pretend like you know what's going on. The other skill, this is an aside, I'm sorry, the other skill that organic chemists use to show off is naming ring molecules that have nitrogens in them. We call them heterocycles. Piperidine, piperazine, diketopiperazine, imidazole, oxazole. You know what, though, the people that are really good at this would be yawning at this point, not because they're bored like you, but because the names are not that impressive. But the more nitrogens you add, the more strange the names are. Isoxazolidenone or something like that, I don't know. Yes, bless, salute. You can look up heterocycle names and try to bust them out at parties. It will not do you very much good unless you're dealing with OChem graduate students. Anyway, sorry. Intramolecular Claisen reaction. We're going to do the same thing we did with the aldol. That is, let's take a molecule that has two esters. All right, so there's a diester. I'm gonna make an enolate, they're identical by symmetry. So I'm gonna make an enolate out of one of them, and then the other is gonna be the electrophile. So here I would use, again, a base that's matched to the group that's on the ester, so that if we did do the nucleophilic acyl substitution reaction, we wouldn't be able to tell. Make the enolate. Fortunately, unlike the intramolecular aldol where we had to think about there being multiple possible aldol products because of the multiple possible enolates that we could form, there's only one kind of alpha proton here, so there's only one kind of enolate to form. The real trick now is, now that you formed the enolate by removing a proton from the alpha carbon, you have to get the right number, you have to count the number of atoms in the ring that you're going to make as enolate attacks carbonyl compound to give you a tetrahedral intermediate. So start with the alpha carbon, 1, 2, 3, 4, 5, 6, ooh, 7. That's fun. So now we have to draw a 7-membered ring and number the atoms 1, 2, 3, 4, 5, 6, 7. Carbon 1 is bonded to the ester and used to be the alpha carbon. Carbon 7 used to be a carbonyl carbon. It's bonded to the negatively charged oxygen of our tetrahedral intermediate and the ethoxy group, which we can kick off. A negatively charged oxygen is a good enough kicker offer group to kick off the ethoxide. And we're left with this 7-membered ring product, which is a beta keto ester. I'm not going to show what happens, which is that ethoxide removes the alpha proton, the one that's alpha to 2 carbonyl groups, and then we gently acidify. I'm just going to show the final product here. Okay, nothing really new there. The only new thing is that whereas in the intramolecular aldol you didn't have a good leaving group, now we, or didn't have a leaving group good enough to leave for a negatively charged oxygen, now you do. Okay, so intramolecular. Got the same issues with the crossed Claisen as you do with the crossed aldol, and same basic workarounds, which we can talk about, but anything you want to say, anything we need to say more about Claisen? Okay. Or the intramolecular version. Yeah. Could you do this with an ester that's not terminal? By that, I mean, if we put something here that was not an ester, it would no longer be an ester. But you're thinking maybe other stuff here? Huh. Oh. Yes, I think that's a decent possibility, though I would be worried here that your base would attack this and do the substitution reaction instead of the Claisen reaction. So yeah, I guess that's possible. I would just be worried about it. What else?
What makes that worrisome versus the other one?
Well, do you remember that I said above we weren't worried about this happening because if it did, we couldn't tell?
Right.
Yeah. If this happens here and this group gets kicked off, then suddenly we don't have the same molecule anymore. Yeah. So your text has some stuff about workarounds for the cross-Claisen reaction. I think it's easy enough that I don't really think we need to spend a lot of time on it. One thing you can do to do a cross-Claisen in a way that sort of prevents undesired side products is to cheat by using an ester that's also an acid chloride. This one can only be an electrophile. So if you do the Claisen reaction with sodium methoxide, you make this enolate, you would get to this tetrahedral intermediate. And now there's two leaving groups attached to our tetrahedral intermediate, and the chloro is the best one. And so that allows you to generate this product, which is pretty specialized. I mean, now you know that reaction, you know the one way there is to make this molecule, which you actually used in chapter 17. This was the malonic ester. But you can see that there's no possibility of this starting material acting as a nucleophile because it has no alpha protons at all. And so that's a common strategy for the cross-Claisen reaction. Yeah?
Is, the last reaction, is ethoxide a strong base?
Yes.
So could that be done with any strong base or just?
Could this be done with any strong base? Yes. The point, though, is that with ester chemistry, if you want to do enolate stuff with esters, the thing that you're always worried about is the potential for attack of your base on the ester. That's why it would not be good to use hydroxide as a base here, because you're going to, in addition to removing the enolate, you're going to do the saponification reaction. See, if you use a base that's matched to the identity of the group on your ester, once you get here, who cares? It doesn't even matter because you can't tell which one attacked and which one got kicked off. Either way, you're going back to the starting material. Yeah. All right, what else?
Will you still get self-reaction products there or not?
Yeah, you would still worry about self-Claisen as a product. I think the idea is that this is a pretty, by virtue of the fact that it has two electronegative groups, that carbon's pretty electron poor. And so I think the hope is that most of your enolate, when it forms, will attack the most electron poor thing. So yeah, you're sort of biasing reactivity by using an especially good electrophile. Okay, so nature has Claisen reactions as well, and they're involved in fatty acid biosynthesis. So, just as well talk about that. Nature's Claisen reaction happens on thioesters rather than esters. I think I mentioned before that you can judge the reactivity of a carbonyl compound by comparing the leaving group ability of the thing that's on the carbonyl compound. So here the leaving group is just an alcohol which has a pKa of like 16. Here the leaving group is a thiol that has a pKa of 8. We could show you the structure of acetyl-CoA. It's basically, or rather, CoA stands for coenzyme A, which is a rather large group that ends in a thiol. So provided you're okay to think of coenzyme A as that, you're all right. We can show you the structure of it. I don't have it memorized, so let's see. Amazon wants to sell me some. Behold, coenzyme A. Naturally, you don't want to draw it. So all we're going to do is the business end of the molecule is the thiol. All of the rest of it is for is sort of a handle for the enzyme to hold on to. You okay with that? Okay, go ahead and forget about it. So when I write S-CoA, I'm literally meaning the sulfur on the end of that and then the rest of it, which we're abbreviating. Okay, so what I've drawn here is called acetyl-CoA. Some biochemists will call it acetyl-CoA, which we will tolerate. But it's an acetyl group, not an acetyl group. At some point, the pronunciation issues get sort of pretentious, so I'm sorry about that. This molecule is a thioester. This molecule is an ester. Based on leaving group ability, the pKa of the conjugate acid of the leaving group sort of tells you about leaving group ability. Thioesters are more reactive than esters. They're not as reactive as acid chlorides, which we could draw here. Nature doesn't use acid chlorides because they're too reactive. So thioesters are great compromise. They're stable in water, which is great because biology happens in water, but they're a bit more reactive than esters. So nature uses acetyl-CoA. Actually, acetyl-CoA is a product of glycolysis and another enzyme. And it is the starting point for, it's the starting point for the citric acid cycle. And if you have too much of it, then your body stores it by using acetyl-CoA to make fatty acids. Acetyl-CoA just has 2 carbons. And that's important because all the fatty acids that your body makes come from these, have even numbers of carbons. All of them come from subunits of acetyl-CoA. All right, so what I'm showing you here is just a couple of the initial steps from fatty acid biosynthesis. Acetyl-CoA comes and it encounters what's called the acyl carrier protein. And I think this is, some of you may be having flashbacks to the exam because something like this showed up on the exam. What happens is trans-thioesterification. You need to get this acetyl group onto the acyl carrier protein, which acts sort of as a crane that delivers acetyl-CoA to various portions of an enzyme, multi-enzyme complex. So what happens at this stage is nucleophilic acyl substitution. We don't need to draw the whole thing, but lone pairs on the thiol attack the carbonyl carbon. You get a tetrahedral intermediate, and then that acetyl group gets transferred to the acyl carrier protein, and then coenzyme A thiol gets liberated and can be recycled and used elsewhere. So this is not the Claisen step. This is nucleophilic acyl substitution. Once you've got the acetyl-CoA on the carrier protein, the Claisen reaction can happen. All right, So now I need to introduce reactive partner number 2, the acetyl group on the acyl carrier protein. I guess I should have used the color orange because that's what we've been using for the electrophile portion of these reactions. This is going to be our electrophile. Now we need a nucleophile. And the nucleophile looks like this. All right. Before we get too far, what do you notice about the structure of that nucleophile? What's its structural pattern, similar to things you've seen before? A beta keto or beta carbonyl acid. And those are prone to decarboxylation. Because if CO2 leaves, if we did something like this, where lone pairs on this oxygen kick down, the electrons in this bond between the acid carbon and the alpha carbon can go onto the alpha carbon where they're stabilized by resonance. So nature actually often uses this beta keto acid as sort of a masked enolate, because as soon as you lose CO2, what you're left with is an enolate. So nature doesn't have to have a base present to make the enolate. It instead just uses the loss of CO2 to generate your enolate. You see what's going on there? Loss of CO2 leaves behind electrons, and suddenly your enolate is revealed. Once that enolate is revealed, attack the carbonyl carbon to get a tetrahedral intermediate. Make a new bond between the alpha carbon of your enolate and the carbonyl carbon of your electrophile. Then electrons kick down and kick off the leaving group, which is that thiol from the acyl carrier protein. And now you've taken something that had 2 carbons and you've elongated it by another 2 carbons. Here was my, oops, that's not what we wanted. Here was my electrophile. Here was my nucleophile. Here's the new bond I made. We're not worrying about what this R group on the ester is, but it is another arm on the enzyme that's going to transfer this now beta keto thioester through a couple of more reactions which we won't talk about yet. One of them is a reduction reaction. We'll deal with that mechanism later. So you reduce to the beta hydroxycarbonyl compound. You eliminate to get the alpha beta unsaturated carbonyl compound, and then you reduce again, basically do hydrogenation to get the saturated hydrocarbon. And all the while, here are the 2 carbons that came from acetyl-CoA. And at this stage, you can take this molecule and start again, attach this molecule to the acyl carrier protein, have another enolate come in and attack, and then you successively tack on additional 2 carbon units. And most fatty acids that are in animal types of fats and oils are in the range of 16 to 18 carbons long. So a single fatty acid chain contains 7 or 8 or 9 individual units of acetyl-CoA. Fatty acid fatty acid degradation or metabolism is the exact backwards of this, and it involves a retroclason reaction. But yeah, the key step that's similar to stuff that you've seen before today is this attack of an enolate on a thioester to get a tetrahedral intermediate, kick off the leaving group, you get a beta ketothioester as a product. All right, more you want to say about that? Make it stop is maybe it. All right. We can do one more, and that'll give us some extra time on Friday to get caught up. We actually are caught up, but that'll give us some more time to deal with examples and try some practice problems. So the final reaction today also has a name. It is called the Michael reaction, but it is basically just conjugate addition. Conjugate or 1,4 addition. You've seen conjugate addition before twice. The first time was with cuprates. We had an alpha beta unsaturated carbonyl compound, and then we had some cuprate. Let's maybe be diphenyl cuprate. And we said that unlike organolithium or Grignard reagents, the cuprate would deliver the nucleophile to the beta carbon. We said that that's possible because resonance tells you that the beta carbon is electron poor. You can draw a resonance structure like this where the beta carbon has a positive charge on it. If you want to take the molecular orbital theory point of view, this is a conjugated pi system involving 4 atoms, and some of the LUMO is on this beta carbon. So it should be reasonable for the cuprate to attack the beta carbon. As to why the cuprate attacks the beta carbon rather than the carbonyl carbon, that's a memorized detail. Organolithiums and Grignards attack the carbonyl carbon. Don't really have a great reason why. The negative charge ends up on the alpha carbon where it is stabilized by resonance. Your phenyl group from the cuprate ends up on the beta carbon, and then you pick up a proton on the alpha carbon during aqueous workup. We won't be very specific about what the acid is. And the product has a new bond between your nucleophile and the beta carbon, and your alpha carbon, which used to be involved in a double bond, no longer is and has a new carbon-hydrogen bond. Okay, so that's conjugate addition reaction number 1. 2, you saw earlier today in the retroaldol reaction where we said that the first thing that happens to take an alpha beta unsaturated carbonyl compound that's an aldol product back to starting materials is to have oxygen attack the beta carbon to give you this intermediate. Okay, so those are two examples of conjugate addition that you've seen. We're going to introduce one more, and that is instead of using a cuprate as a nucleophile or OH minus as a nucleophile, we're going to use an enolate. It's almost as though somebody stayed up late at night plotting to make this as horrible as possible by bringing all the terrible things together in new and painful combinations. If you think this is bad, wait till Friday, when we introduce the Robinson annulation, the single longest mechanism you will learn in 352. You should not be afraid. It is really not that bad. It just combines a lot of things you've seen before. So, as an example, let's use this enolate and this alpha beta unsaturated carbonyl compound. This has the potential to be messy, so I'm choosing my examples here deliberately. In general, your text shows in terms, well, let's just pause there. Here's your enolate. Here's your alpha beta unsaturated carbonyl compound. You're going to do just what we did above for cuprates or for alcohols. The enolate attacks the beta carbon. The beta carbon is electron poor. Why doesn't the enolate attack the alpha carbon? I'm sorry, the carbonyl carbon. If it did, that would be an aldol reaction. I don't know. In general, if you have an enolate and an alpha beta unsaturated carbonyl compound, you're going to do the conjugate addition reaction. The new bond we make in a conjugate addition reaction is with the beta carbon, between the beta carbon of your electrophile and the alpha carbon of your nucleophile. Okay. So here was my nucleophile. Here was my electrophile. And here's the carbonyl carbon of my electrophile. Or sorry, my nucleophile. Here's the alpha carbon of my nucleophile. We're making a bond between the beta carbon of the electrophile and the alpha carbon of the nucleophile. In a subsequent step, we're going to pick up a proton from the conjugate acid of our base that we made the enolate with. And our product is going to be this. Again, this is the new bond that we made between the beta carbon of our electrophile and the alpha carbon of our nucleophile. But, and we'll call this a Michael product. If you want to get good at recognizing Michael products, there's a couple of ways to do this. One is to note that the carbonyls are now 5 atoms away from each other. So a Michael product is a 1,5 dicarbonyl compound. And then another, so between that and identifying the bond between the beta carbon of your electrophile and the alpha carbon of your nucleophile, and then looking for the pattern of carbonyls that are 5 atoms apart, that's about it. Okay. So I think that's gonna clearly take some practice. Go ahead.
Is it only that diketone that could do that, or?
You could choose any, yeah, the question is it only this diketone that can do this? You could choose any enolate you want. The problem gets into if you choose this, well, is that going to do an aldol with itself, or is that going to react with this one? There's just a lot of complications. I've noticed in your text that most of the examples of a Michael reaction start with a nucleophile like this, and I don't know why. There's not really a lot of explanation. The best place for a question about the Michael reaction is not a predict the products question. It's either a synthesis where they show you this and say, how could I have made that? Or it's a mechanism question where they show you the starting materials and the products and you have to push arrows to get there. So it's kind of tough to ask an open-ended question about the Michael reaction because there are some other legitimate possibilities. So we're going to keep questions about this reaction to either synthesis, here's where I want to end up, how did I get there, or mechanism, here's what I started with, here's what I ended with, how did I get there? All right. All right, so that about does it for today.